For this lesson in fluid mechanics, I'll be discussing the continuity equation. The learning objective is to define fluid flow and understand how conservation of flow can help one determine fluid velocity or the cross-sectional area of fluid conduits. This will be the first lecture that truly moves out of fluid statics or the science of fluids at rest and into the domain of fluid dynamics or the science of fluids in motion. Let's take a round pipe that serves as the conduit for some liquid, and suppose it varies its size along its course. The fluid here is moving left to right. Fluid flow is defined as the volume of fluid that moves past a certain point per unit time. It is mathematically represented as Q, which for some reason stands for flow, and equals volume divided by time. This is a powerful relationship in itself, but it also leads directly to the focus of this video. We'll take an arbitrarily long section of narrow pipe here, and we'll define the cross-sectional area as area 1 and the length of the section as L1. From what we have just learned, Q1, or the flow of fluid through this segment, will be equal to the volume divided by time. We know that the volume of a cylinder is equal to the cross-sectional area times its height, or in this case, V1 equals A1 times L1. That seems straightforward enough, but look, we can group these a little differently, and length divided by time is a velocity. So this results in the flow through section 1 is equal to the cross-sectional area of section 1 times the velocity of fluid moving through section 1. With identical analysis, if we define a section 2 in the wide part of the pipe, we will quickly determine that Q2 is equal to area 2 times velocity 2. The key realization here is that the flow in section 1, that is how much volume passes through section 1 per unit time, must be equal to the flow in section 2. If these were not equal, fluid would back up somewhere and become very compressed, and this would violate the assumption of elementary fluid mechanics that liquids are non-compressible. So if Q1 equals Q2, then we can say the product of A1 and V1 is equal to that of A2 and V2. This is what's referred to as the continuity equation. This is the simplified form appropriate for non-compressible liquids. You can think of it as a statement of conservation of flow, which is really the law of conservation of mass as applied to moving fluids. That is, what passes through section 1 must pass through section 2. Volume of fluid isn't lost or created somewhere in between the two. Compressible fluids also have a continuity equation, but it's a bit more cumbersome and with few applications outside of physics and engineering. Let's do two examples. Suppose we have a fire hydrant and we hook up a fire hose and turn it on. The radius of the outlet of the hydrant is 2 centimeters and water is passing through it at 4 meters per second. The radius of the nozzle is 1 centimeter. Given all of that, what will be the velocity of water as it exits the nozzle? Sounds like a continuity equation problem, so we'll start with area 1 times velocity 1 equals area 2 times velocity 2. The areas are pi r squared. Substitute in our known values and pi cancels. This leaves us with a velocity of 16 meters per second. Let's take an example that has a little more of a medical aspect. In an adult, the aorta's radius is normally 1.5 centimeters, and blood moves through it at an average speed of 30 centimeters per second. If the typical capillary has a radius of 5 times 10 to the negative 6 meters, and blood passes through them with a velocity of 0.1 centimeters per second, approximately how many capillaries are in the body? Again, another continuity equation problem. In this case, area 1 is the cross-sectional area of the aorta, and velocity 1 is the average speed of blood in the aorta. But what is area 2? It is the total cross-sectional area of all capillaries, which is the cross-sectional area of one capillary times n, where n is the total number of capillaries. Substitute in the known values. Pi cancels out. And solve for n. To make the arithmetic just a little more manageable, we can distribute the second power and rearrange terms. And with the help of a calculator, we determine that there are approximately 2.7 times 10 to the 9th capillaries in the body. The continuity equation is used in other places in medicine, most prominently in the field of echocardiography, which is the study of ultrasounds of the heart, where it is routinely used to calculate the area of abnormal heart valves. We'll talk more about echocardiography in the next lesson on the Bernoulli equation.